23. Okay, so we've talked about secant lines, we've talked about tangent lines. We're going to kind of formalize it in the notes today. So if you have a secant line, it is intersecting at 2 points. So that's what this is right here. Because that's the best we can do in pre-cal, right? But we want to get those points closer and closer together, so close that it actually eventually becomes 1 point when we get into calculus. And if it intersects just at 1 point, what is that line called? What is it? Starts with a T. Tangent. So this is the tangent line. And I'm going to clarify a little bit of stuff here. So you got a secant line that intersects at 2 points, tangent line that intersects at 1 point. We kind of talk about both as we're talking through these things. The secant is what we're using to approximate it. The tangent would be what we would have if we could actually find it exactly. But in geometry, you are taught the definition that a line tangent to a circle intersects a circle at exactly 1 point. And that word exactly is pretty important because you can't come back around and intersect the circle again, right? Well, that's a line tangent to a circle. I'm not sure that what I'm about to explain to you is actually going to even come up for us, but just in case, I don't want you being confused about tangents and whatnot. So now that we're talking about them on functions and so forth, and you don't have to draw this, just kind of stay with me. If I have a line that is tangent to this, well, that's fine. If I have a line that's tangent to the function at this point right here, because that's where I want my rate of change, will that line intersect this function again? It will, right? But the definition of a tangent line isn't that it just intersects a function even just at exactly 1 point. That's true for a circle. It's true for some functions. It's not true for all of them. But I could also just draw a secant line like that and call it a secant line. The difference here is that when we're talking about the lines actually tangent to the functions or even secant, because even if I drew a secant line through these 2 points, it would still intersect like at a third point over here, right? We're looking at it just with it like a restricted domain, like maybe just between these 2 lanes. And I'm only looking at this right here. I don't really care about anything else. So when we're talking about it only intersecting at 1 point, we're talking about in its little neighborhood of points, just relative to the points like right around it. Okay? Do you see the difference there? So I just don't want you to think if we draw a little tangent or secant and it's on a function like this, that, well, it is going to cross again, so that doesn't make it tangent. That's not true, because it's kind of a different way to look at it. So we only care about it being tangent like right there, just right at that little spot. Okay. So let's go back over here. So it says a secant line joining 2 points of a function. We finding the slope of the secant line. We know that, and look at this notation again like we were doing yesterday, and that's the average rate of change over this interval. Average rate of change on the interval. We've called it we've called it AROC. We know that it's delta y over delta x. M means slope. The little subscript there means it's the slope of the secant line. And again, same notation and stuff we were using yesterday. Okay, we good? All right, so now let's look at a line, because today we're talking about linear and quadratic functions specifically. So it says, consider the graph at the right. It passes through these points, 0, -3, and 4, 3. Then it says, explain how you know its equation is this. Well, we know how to find slope, right? Our slope is our delta y over delta x. They gave us 2 points, so I can do my slope. I can do 3 minus a -3. So 3 minus a -3 over 4 minus 0. That'll give me 6 over 4, which becomes 3/2. So that's where my slope is. That -3 in that equation, what does that represent in the equation? The y-intercept. And then what letter do we use for the y-intercept? What is it? B. Okay. So then we know that B is the y-intercept, and that is -3. And then we know how to use y equals mx plus b. Okay. So y equals mx plus b. That's your slope-intercept form. We only use that if we are actually given the y-intercept. Not if we can figure it out, not if we can guess it off the graph. If you are flat out given the y-intercept, y equals mx plus b is good. Otherwise, it's junk, okay? Point slope form is the way you want to do everything. And I will make you a believer. I understand that you probably dealt with this form a whole lot more in Algebra 2 than the point slope form, but that's the one that you have to know and love and it become your thing. That one will just make your life way more difficult, even if you don't believe me right now. Okay, so then it says, what do you notice about the average rate of change of the linear function? What's true about it? How is it different than an average rate of change for a quadratic or anything else? It's constant, thank you. It is constant. It does not change, right? That's what makes it a line. That's what makes everything we're doing right now a little bit different and weird for you because our rate of change is changing and that's not something you've really looked at before. So how is the average rate of change related to the equation itself? Okay, so here's what I'm asking with that because you could say a whole lot of things here. So I want to say, let me make sure I use my words right. Yeah. For every 1 unit, x increases y increases by how much? What do you think? It's a different way of talking about slope. Because I know you know rise over run. If I go up 3, I go over 2. But this is saying if x increases by 1 unit, y increases by how much? Look at your graph. If x gets bigger by 1, how much bigger did y get? Goes to like right there, right? How much is that? Where would that number come from? 3/2. If x gets bigger by 1, y goes up 3/2. X gets bigger by 1, y goes up 3/2. That's what your slope really means, but then we talk about it as rise over run because it's easier to count. Y increases by 3/2. Okay, gotta kind of understand the concept of both there. So then it says, use the grid at the right to sketch a graph of the function that represents the average rate of change of the linear function. So we're going to graph a function that represents the average rate of change. Well, we know what the average rate of change is, right? Your average rate of change is equal to delta y over delta x, which is 3/2. I need my graph to represent that no matter what the x value is, the average rate of change is 3/2. So I can make an equation that says y equals 3/2. That's not a statement like I solved for something. That's an equation of a line, right? This is a linear equation. That represents the rate of change. So how do you graph a line y equals something? Is it horizontal or vertical? Horizontal. And if you don't know the difference between horizontal and vertical, that's a bad thing. It is horizontal, and it's saying that y is 3/2. Y is always 3/2. It looks like this. So when x is -4, the rate of change is 3/2. When x is 1, the rate of change is 3/2, which should make sense because the rate of change is the same for the entire line because it's a line, right? We good with that? Little side note of horizontal and vertical lines. Ms. Ludicky showed me this like, I don't know, 15 years ago. It's been a long time. But if I draw a lowercase cursive y, like elementary school, like, you know, you're supposed to write it or whatever, and then I flip my paper upside down, and you may need to do it on the side of your paper to see, because I can't flip my board around. But then if I flip my paper upside down, what's it going to look like? An H. And that means that the y equals lines are horizontal. If I have an x, if I flip it upside down, what's it going to look like? An x. It's not going to be very exciting. But if I chop it in half, I get a v, and those are vertical lines. X equals vertical, y equals horizontal. Don't ever mess that up ever again in your life. Not that any of you would today, but I know some of you would have. So that's a life skill there that you need. Okay. So we good with that? Constant rate of change, we have a constant linear function. Yes? Now we're going to look at quadratics. So, oops. Oh, dang it. I've got to fix that. It doesn't record right. Hit the wrong thing. Oh, there we go. Okay. So I'm given this quadratic function. I am also given a table of values, so I don't have to actually calculate them. They're calculated for me. And the graph is drawn and everything. But we're going to use the table of values to find the average rates of change on consecutive equal length intervals of x values. What does consecutive mean? Like one right after another. Like Monday, Tuesday, Wednesday are consecutive days. Monday, Wednesday, Friday or not. Are not. They go right one right after another. Equal length intervals. So you'll hear that a lot. Meaning that I'm not going to find the average rate of change between 0 and 1 and then between 1 and 4 because those intervals are not equal to each other, okay? So we're going to find it between 0 and 1 and then 1 and 2. So in the intervals, we're going to write it just for these notes purposes to understand what we're doing, but then we're not going to have to write it like this again, okay? So my first interval is going to go then from 1 to 2, and they're all inclusive here, and then from 2 to 3, and so forth and so on. 3 to 4, 4 to 5, 5 to 6. So my average rate of change is slope. It is the change in y over the change in x. Between 0 and 1, what's the change in x? 1, right? Each one of these up here has a change of 1, right? So change of y over change in x, I really only care about my change in y because it's going to be over 1. Does that make sense to you? Why we only care about the change of y? So then when I do my average rate of change is going to be the change in y. Between 0 and 1, I'm going to do 0 minus 5. It gives me negative 5. Negative 3 minus 0 gives me negative 3. Negative 4 minus a negative 3 is what? Negative 1. Negative 3 minus a negative 4 is 1. 0 minus a negative 3 is 3. 5 minus 0 is 5. So look at your average rates of change. As the x increases, what is happening to your average rates of change? They increase also, right? They're adding to you. I heard that, but yes, because they're increasing. So since my average rates of change are increasing, what does that tell me about my function? When your average rates of change increase, your function is what? Concave up. And if they're decreasing, it's concave down, right? The function itself is decreasing until we get to 3 and then increasing, right? But the average rates of change are increasing throughout the entire thing, and that is what makes it concave up. Okay, we good with that? All right, are they increasing at a constant rate? Yes, they are, okay? So let's answer this question. It says, using the results from the table, the average rates of change above, do you notice a pattern in the rates of change? So we'll say yes, or hold on, yeah. As x increases, okay, now we've been abbreviating average rate of change as AROC. That's fine in our work and our explanations. We have to write it out because there's some question about whether or not College Board will allow an abbreviation like that. I think that they will, but it's not worth the risk. So we're just going to do, as x increases, average rates of change of, is this called F? Yeah, of F increase. Okay, that's all it really asked. I asked you some other questions, but that's all that really asked. Then it says, what can you say about the rate of change at x equals 3? Well, at x equals 3, there's that tangent line, or my secant line. What is the slope of that line? That is the equation of the line, yes. But what is the slope of the line? 0, the slope of the horizontal, yeah. So, yes, the equation is y equals 4, very good. But the slope is 0, okay? So then I can say at x equals 3, the rate of change is 0. Notice I didn't just put 0. Like, we've got to write outwards. Everybody okay with that so far? Okay, so we're going to do one more thing on this. We're going to look at the change in the average rates of change, which somebody has already said, and that's totally fine. But -3 minus a -5 is 2. -1 minus a -3 is 2. 1 minus a -1 is 2. 3 minus 1 is 2, and then 2. Okay? So your average, the change in the average rates of change is constant. Okay? This tells us a couple of things. These are our first differences. These are our second differences. So the fact that they're the same tell me that it's a quadratic. That also gives me the slope of every single one of these little secant lines that I could draw along here. All right, so let's look at what I mean by that. So it says, using the function from example number 2, let's consider what the graph of the average rate of change for this quadratic function would look like. The parabola is concave up. We talked about that. Because the average rate of change, and again, average rate of change, equal length intervals, you'll hear that a lot. The average rate of change on the equal length intervals is increasing by a factor of 2. So that's the slope of our new function, like I said. We also observe that the quadratic function changes from decreasing to increasing at the vertex, where x is equal to 3. So at x equals 3, we have that horizontal line, so the rate is 0 here. And we say that slope is constant. Okay. So here's what we're going to do. We have the graph of the parabola. We're going to graph the average rates of change. Just like we had the linear function, we graph the rate of change, which was always 3/2. This rate of change changes, but it's linear because it has a constant slope here. So we're going to be able to come up with this. It tells us to use the ordered pair x value, comma, rate of change. That means that we know this. We know that we have a point on our new line that is at 0. Nope, it's not. It's at, oh my God. Erase already. It is at 3, 0. Okay? Because when x is 3, the rate of change is 0. Okay? We also know that those rates of change at a constant rate of 2. So we're going to write an equation of a line with that using the point slope form, which is y minus y1 equals m times x minus x1. Okay, so let me show you why this is really easier in the long run. To do this, my x and y is a 3 and a 0, so it's going to be y minus 0 equals 2 times x minus 3. If all we had to do was write our equation, we're done. We don't care what b is. We don't care about y equals mx plus b. We are just done. All right? And in this one, these numbers are pretty nice, and it's not that big of a deal. But have you ever done y equals mx plus b, and they're like horrible fractions, and you had to do weird stuff with fractions? Like, this avoids all of that. Now, because I want to graph it, I can graph it from here, but I don't want to make your head explode today. It's actually easier than the other, but I know you don't think so. So we can go ahead and take this one, since it's pretty simple, and put it into y equals mx plus b. But I'm only doing that because I want to graph it. Otherwise, like I said, we could have stopped. So y minus 0 is just y. When I distribute the 2, I get 2x minus 6. I can easily graph that. So I have my y-intercept at -6. My slope is 2, so I can go up 2 over 1. And then I also have this point here, this 3, 0. So I really have 3 points I can plot easily. And then pretend like I went through that point because I'm not redrawing it. There's your line. So let's talk about what this means. We have that 3, 0. Let's look at these other ordered pairs we actually plotted. We plotted 0, -6, and we plotted 1, -4. That tells me for my parabola, when x is 0, my average rate of change is -6. When x is 1, my average rate of change is -4. Let's go back to the parabola and look at that. We already know that at 3, the rate of change is 0. But when x is 0, here's my point when x is 0, right? I'm right there. That rate of change, that is -6. That's the slope of that tangent line right there. When x is 1, right there, that slope is -4. That's what those ordered pairs mean. And that's what that graph is giving us. Okay? So we took the line, the linear one, we graphed the average rate of change, it's constant. For your parabola, when we graph the rate of change, it is, oh, I moved the thing again. I gotta move this or I can't get to it. Then the average rate of change, the function is linear right here. Okay? We good so far? All right. I'll take that as a yes. Okay, so over any length input value of the interval, the average rate of change for a linear function is constant, graphed as a horizontal line. Given consecutive equal length input value intervals, the rate of change of a quadratic can be given by a linear function. And the average rate of change over a closed interval is the slope of the secant line. In a quadratic, or really any of these functions, we can determine the curvature or concavity of the graph by, it says considering, it should say considering, the average rate of change, and again, over equal length x intervals. That equal length is important. Tells us to sketch the secant lines. They're going to look more like tangent lines because it looks like single points. Just pretend like they're 2 points, like really, really close to each other. And when we do that, so if I sketch all these in like this, right? Those represent my rates of change. Are these rates of change increasing or decreasing? Increasing, and that makes this function concave up. So concave up, slope is increasing. Then this would be concave down. And slope is decreasing. Also notice that when it's increasing, the little line segments are underneath the graph, and when it's decreasing, the little line segments are on top of the graph. Okay, just another way to kind of look at it. All right, so now we're going to look at how we graph these things to help you kind of understand how it all went together, but then most of your assignment is going to be looking at these tables, right? We're only going to do A and B. I'm telling you that because there's not a whole lot of room to write. Well, there's some, but there's probably not enough, and I apologize for that. So you might have to like write down the side, and y'all know how to make things fit, right? But we're only going to do A and B, so if you take up some room over there, it's fine. All right, so it would help if I saw the question one. It says, determine if the function could be concave up, concave down, or neither over its domain. Determine if the function could be linear, quadratic, or neither. So the first thing you need to do on any of these kinds of questions is look at your change in x. So when I do this, 1.1 minus 1, that's 0.1, that's 0.1, that's 0.1. If they're the same, so these are consecutive equal length intervals, then we only have to look in the changes over here. If these are different and they're not the same, then you would have to actually calculate the slope using the change in the x over the change in the y. Okay? But because they're the same, I don't really care about what these values are specifically. We just want to look at the patterns in them. So since these are the same, let's look at these differences. 1 minus 4 is negative 3. Negative 1 minus 1 is negative 2. Negative 2 minus a negative 1 is negative 1. Okay? So the first question said, determine if the function could be concave up, concave down, or neither over its domain. These are your average rates of change. Are they getting bigger or smaller? Bigger. They're increasing, right? Getting closer to 0. So they're increasing, which means is this concave up, concave down, or neither? Concave up. If it's increasing, it's concave up. So my answer is concave up. Okay, then I have to explain myself. Then I can say rates of change. Oh, average, AVG. Average rates of change of K are increasing. Okay, that's how I know. You can't just say concave up. You also have to say, like, how do you know that? It's because the average rates of change of K are increasing. Okay, we okay with that? All right, so then the second one said, determine if the function could be linear, quadratic, or neither. So then I'm going to look at the second differences. So these are the first differences. These are going to be the second differences. So negative 2 minus a negative 3 is what? 1. Negative 1 minus a negative 2, 1. When your second differences are constant, you remember this from Algebra 1, that means you have a quadratic. So this is a quadratic. And our reason is the second differences of K are constant. Okay? First differences, second differences. We okay with that? Questions? All right, let's look at B. So I'm going to look at this again. This is 0.1, 0.1, 0.1. So they're all the same. Since they're all the same, I don't have to go through the whole slope process. I can just look at the differences here. So 4 minus 1 is 3. 7 minus 4 is 3. 10 minus 7 is 3. So my average rates of change, are they increasing or decreasing? Neither. What are they? Constant. So it can't be concave up or concave down, right? So my answer, and neither was an option, so my answer is neither. And then I say the average rates of change of M are constant. Okay, so my first differences are constant, and since it can't be concave up or concave down, what does it have to be? Linear. So the answer to the second part is linear, and you can say the first differences of M are constant. Does that make sense? Do you understand what I mean by first differences and second differences? And literally that's something you do in Algebra 1 to figure out if things are linear or quadratic. So.